Hi students, welcome to my lectures on chemical reaction engineering. In the today's lecture, we are going to discuss about another continuous reactor which is called plug flow reactor. In the last class, we have discussed about the continuous stirrer tank reactor in which the reaction happens in a vessel fitted with a stirrer where the proper mixing takes place. Here it is a straight tube kind of reactor where reactants comes from the one end and the product is coming from the another end going. Somehow we have to design what volume of this reactor is required for a given conversion. The approach is the same, we do the mole balance and finally we found one equation in which we can able to find out the volume of the reactor for the given conversion. The problem is in case of CSTR, that is in a tank, because it is fitted with a stirrer, everywhere the concentration will remain the same because reaction happens at a same concentration because of the stirrer. Here there is no stirrer, it is a kind of straight tube. At the entrance the concentration of the reactant is different, at the exit the concentration of the reactant is different. That means the rate will happen at high speed at the entrance because the concentration of the reactant is more, so the rate of reaction is more. At the exit, as the A molecules getting reacted, the concentration of A will get reduced at the exit, so the rate of reaction will be very less. Higher rate at the beginning, lower rate at the end or near exit. On what rate we have to proceed the mole balance? I mean, somehow we have to, how fast the A is consuming in the reaction, we have to take out some term, right? But on what speed, whether you wanted the early rate or the late rate, which based on which rate you have to design your reactor. That is why you have to somehow average the rates between the entrance and the exit. So we use the integration, okay. Integration means averaging the rate over entire volume. That means it neither takes higher rate nor takes lower rate, it somehow average the rate of reaction. That is why whenever you see the design equation in future for the plug flow reactor, the integration symbol will come. In the CSTR there is no integration because at every location the concentration is same. That is why you do not have to average the concentration. Here, because the concentrations are different at different locations, you have to somehow take the average. That average is nothing but the integration. So let us proceed. There is a different way to approach this problem. If Fa0, Ca0, Va0 are the initial molar flow rate, concentration and volumetric flow rate, Fa, Ca, V are the exit molar flow rate, concentration and the volumetric flow rates. You have to somehow take the small section here and differential section, that is you have to take a small section, apply the mole balance on the small section and you integrate. So that you can already if you integrate, right, that means it will automatically take the average of the entire reactor. So let us take a small section, this cut section of a differential volume delta V or dV, whichever thing is you talk about. The inlet to this differential section is Fa at V because this position is V and this position is V plus delta V. Okay. Let me put this on the board. This position is V, this position is V plus dV or delta V. Okay. Now this entrance is flow rate of A at V and exit is flow rate of A at V plus delta V. Okay. Now this is our, now apply the mole balance on this section and integrate over the entire volume. The same moles in minus moles out, plus generation minus consumption is accumulation. I told you in the flow reactors, normally everything happens at a steady state. With respect to time, things will not change. So, that is why the accumulation term is 0, because everything is flowing. And as I am doing the mole balance on my reactant A reactant never generate in the reaction, it will always consume. So, that is why this term is 0, and rest inlet, outlet minus consumption equal to 0. These are the only 3 terms will be there. Inlet is Fa at V, outlet is Fa at delta V, consumption is minus Ra into delta V. Okay, minus Ra into, because minus Ra is the how fast the A is getting reduced in the reaction. The unit of R is moles per liter into second. Delta V, the volume units is liter. The liter cancels, it will also moles per second. That is, this is in moles per second, this is in moles per second, and this is in moles per second. Now, take out the rate on one side and rest on the another side, and take because you have taken a differential volume, let us apply the limit as this volume tends to 0. That means as delta V, that means as this become different, as this volume is becoming differential volume, and you can apply the method of differentials, and Fa at V plus delta V minus Fa at V by delta V. This term, as the limit delta V tends to 0, will become dFA by dV. So, minus dFA by dV is equal to minus Ra. Now, take volume on the one side and rest everything on the other side. So, volume on one side minus dFA by minus Ra is on the another side. Apply the limits. That means you are doing the integration. Now, you are doing averaging. Now, you know the differential section. Now, you have to integrate to bring the average term. Now, 0 to V, that means from here to here, 0 volume to V volume, because volume of the reactor is V. The initial flow rate is Fa0, exit flow rate is Fa. So, that is why 0 to V, Fa0 to Fa. Therefore, the V is equal to, if I take out this minus symbol, this limits will flip. Okay. So, think of Fa to Fa0 dFA by minus Ra. This is your design equation. This is how you can able to find volume of the plug flow reactor. If you know this term, integrate this term, then you get a value that is nothing but the volume of this particular reactor. Similarly, in terms of conversion, I know Fa equal to Fa0 into 1 minus x, dFA is equal to minus Fa0 into dx. Simply we substitute this in this equation, we get volume is equal to, at Fa, that means at this position the conversion is x, at here the conversion is 0. So, that is at Fa place it will become x, at Fa0 it becomes 0. Therefore, now you get a one more minus symbol. So, if you remove the minus symbol, you have to flip the limits. That means 0 to x, Fa0 into dx by minus Ra, which is nothing but volume. These both are generalized equations. Okay? That means it applies to any order equation. This is in terms of f, this is in terms of x. As we have discussed in the CSTR in my previous lectures, let us divide two different cases. One is, there are some reactions the volume change will not happen, there are some reaction volume changes happen, because the volume changes will not happen in a liquid phase reactions, the volume changes happens in a gas phase reactions. As I discussed, 1 mole of A is giving 1 mole of B, there is no issue. 1 mole of A is giving even 2 moles of B, that means suddenly the moles increased because of the reaction, suddenly the volume increases, volumetric flow rate increases. In that cases, the exit volumetric flow rate will not be equal to the initial volumetric flow rate. That typically happens with the gas phase reactions. Now, let us discuss about the liquid phase reactions on one side, gas phase reactions on the another side. For the first order reaction, okay, epsilon, any value, as I discussed in the last class, what is epsilon? epsilon equal to 0, epsilon positive, epsilon negative, as long as it is a liquid phase reaction, it does not matter. Ca equal to Ca naught into 1 minus x minus Ra equal to Kca, K into Ca naught into 1 minus x. Put equation this 4 in equation 3, you get volume term. So, finally the volume is nothing but, if you rearrange and shuffle the equations, volumetric flow rate divided by rate constant into integral 0 to x dx by 1 minus x. You know, integral 1 by 1 minus x is nothing but minus ln 1 minus x. So, minus ln 1 minus x. So, if you take this minus symbol on inside, then total final volume of this reactor, first order reaction, liquid phase reaction, then the volume of this particular for a given conversion is given in the equation number 5. If you know the volumetric flow rate, you know the rate constant, you know what conversion you are targeting, accordingly what volume of the reactor is required, you can get it from this equation. And the same plug flow reactor, if a gas phase reaction is happening, that means final volume, initial volumetric flow rate will not be equal to final volumetric flow rate, that is those are the cases the epsilon not equal to 0, okay, minus Ra equal to Kca first order, Ca equal to Ca naught into 1 minus x by 1 plus epsilon x. This 1 plus epsilon x comes when in case of gas phase reactions where epsilon not equal to 0. Now, substitute Ra equal to K Ca 0 into 1 minus x by 1 plus epsilon. Now, you simply substitute this equation 7 and 3, you get volume, okay, is the integral Fa naught into x by K Ca naught into 1 minus x by 1 plus epsilon x. Now, you know Ca 0 is equal to Fa 0 by V 0. Now, put equation number 9 in equation number 8, you get this equation. Now, you have to integrate this expression. This is the integration procedure. Simple, I have divided this into two terms, integral 0 to x 1 by 1 minus x dx plus epsilon into integral 0 to x x by 1 minus x into dx. X, you know, ln 1 by 1 minus x integral in nothing but minus ln 1 minus x, okay. Let us keep that aside. Now, x by 1 minus x you can get in this form, minus 1 minus 1 by x. If you do 1 minus 1 by 1 minus x, if you do that, you get this term with a negative symbol, do not worry about it. Epsilon 0 to x, x by 1 minus x, x dx is nothing but minus epsilon integral 0 to x 1 minus 1 by 1 minus x. If you do this, you get this expression. I have done the partial fractions. Now, you separately integrate, okay. Now, you separately integrate. You get one term from this part, second term from this part. Then you get volume is nothing but volumetric flow rate divided by K minus ln 1 minus x minus epsilon into x plus ln 1 minus x. Now, if you take out this, take this minus to the power of ln 1 minus x minus 1, and that will become ln 1 by 1 minus x. You can see here, it is the same term. Here also you get the same term. In addition to this term, you get this one minus epsilon into x plus ln 1 minus x. If you know the epsilon, if you know the conversion, if you know the rate constant and volumetric flow rate, you can able to calculate the volume. Similarly, you can able to calculate the space time. Here also same. How much time it requires one reactor volume of the feed to come outside, okay. If it is a 1 liter reactor, how much time this 1 liter volume takes to come out of the reactor. If a reactor is 2 liters, how much time that this 2 liters comes out of the reactor, okay. That is what the space time. Now, you can use this expression to calculate the volume, you can use this expression to calculate the space time, and it is similar way. Here also space time, here is the volume. Let us do a small problem to understand how we can able to estimate the volume and the space times for the plug flow reactor. Thank you. Let us do the small example that what we have discussed few minutes before. One is, let us calculate the volume required for necessary conversion for liquid phase reactions and volume required for the necessary conversion for the gas phase reaction in a plug flow reactor. Given A gives rise to 2B and it is a liquid phase reaction happening in the reactor, and it is given it is a first order reaction. Given inlet molar flow rate is 2 mole per second, volumetric flow rate is 0.1 liter per second, rate constant of the reaction is 0.016 per second, and conversion is 0.5. That means given the data, I have to find out for this 50% conversion what will be my volume, what is the space time, and what is my exit conversion. Okay, and let us do that. I know initial concentration is equal to initial molar flow rate by initial volumetric flow rate, that is nothing but 20 mole per liter. If you remember the equation number 5, and V equal to volumetric flow rate divided by rate constant into ln 1 by 1 minus conversion. If you do that, the volume is 4.3 liter. That means volume of the plug flow reactor is required for 50% conversion is 4.3 liters is required. Space time nothing but volume by volumetric flow rate, and it is at a 43.3 seconds, that is 0.7 minute. That means this 4.3 liter to come out of the reactor, it takes around 43 seconds or 0.7 minute, that is what the space time. Exit concentration is nothing but Ca0 into 1 minus x, okay, that is 20 into 1 minus 0.5, that is 10 mole per liter. And here, I mean, just a second, by 1 plus epsilon x, okay, that is divided by 1 plus 1 into 0.5. This is what I forgot. Fine. Same reaction happens in the gas phase. Let us see the epsilon. 2 minus 1, that is 1, that is not equal to 0. That means initial volumetric flow rate will not be equal to the exit volumetric flow rate. Given Fa0, if I assume the same reaction happening in the reactor, now it is in the gas phase. Now given molar flow rate, volumetric flow rate, rate constant and the conversion, what is the initial concentration? Is nothing but 20 mole per liter, and you have to use the equation number 9 to estimate the volume, because the gas phase reaction. Now you know everything, substitute, you get 5.5 liters. See, for the same conversion in the liquid phase, you need 4.3 liters. For the same conversion, and you need more volume, okay, and volume, space time, nothing but 0.91 minute. Here 0.7 minute the space time, here 0.91 minute, okay. The volume is also increased, the time required for the reaction is also increased because of this gas phase. Similar exit concentration you can measure Ca0 into 1 minus x by 1 plus epsilon x, you find out the value here, okay. And this is what the important. Why this happens? Why for the same conversion more volume is required for the gas phase? Because now more moles are producing here, the gas phase, 1 mole is giving 2 moles. Suddenly the moles increased, volume increased. If you volume increase, what happens? Concentration will reduce, because concentration is equal to moles by volume, okay. Like that, if the concentration is reduced, automatically the speed of the reaction is reduced. Ultimately the rate of reaction is nothing but proportional to concentration. If concentration is more, the speed is more, the concentration is less, speed is less, automatically because of the production of more moles, and many parameters are involved, okay. I hope now you understand how to estimate, okay, the reaction volume for the liquid phase reactions and volume for the gas phase reaction. Let us meet up with the new lecture.